So real op-amps have input impedance which is somewhat less than ideal, and this results in input currents flowing into their inputs. We can define these input currents IN and IP, and we can work out their effect on the output of the op-amp by considering them each in turn. So if we start with IP, the current flowing into the non-inverting input of the op-amp, that's going to generate a voltage VP, which will be equal to minus IP times RP. That voltage VP will effectively see a non-inverting amplifier, and so we will have some output V out, which will be equal to the gain of the non-inverting amplifier, 1 plus R2 over R1, multiplied by VP. Similarly, if we now ignore the current flowing into the non-inverting input and consider IN, the current flowing into the non-inverting input, so in this case VP will be 0, so the voltage at the non-inverting input will be 0 as well. This means we're not going to get any current through R1. Why? Because both ends of R1 are at 0 volts, and we can't have a current flowing without a voltage difference. So all of IN needs to flow through R2. This will generate an output voltage of IN RP, and we can find the net output voltage, the total output voltage, due to both N and IN and IP if we take the sum of these individual contributions. Now, I want to explore this output voltage a little bit, and I want to do that by rearranging my equation. I'm going to put it back to front. Sorry, this should be an IN R2 there. So we've got IN R2. VP we decided was minus IP RP, so I'll put that into the equation. I'll have V out as IN R2 minus 1 plus R2 over R1 times IP RP. And now this gain equation, 1 plus R2 over R1, I want that to apply to all of the terms in this equation, so I'll bring it out the front. 1 plus R2 over R1, there we go. I've got IN R2 divided by the gain, 1 plus R2 over R1, minus IP RP. Now, this term here, I've got a denominator in my denominator. That's a hassle, so I'll multiply those terms by R1. I'm left with my gain. R1 is going to go to the numerator here, so I've got IN R1 R2 over R1 plus R2 minus IP RP. We can make another simplification. We can realize that that fraction there, well, that's just R1 in parallel with R2. And so we can simplify our equation one more time, and I promise it's the last. We've got 1 plus R2 over R1 multiplied by IN times R1 parallel with R2 minus IP RP. And this is a significant result for us because it says that, hey, if we're just sensible about the value we choose for RP, that's that value there, we can remove the effects of much of these input currents. So we will choose RP equal to R1 parallel to R2, and that will greatly reduce our output voltage. It won't bring it to 0. We will still have some output there, which will be given by 1 plus R2 over R1 multiplied by RP, or if you like R1 parallel R2, multiplied by our offset current IOS. Remember, IOS is the difference between our input currents, but this is typically much less than our input bias current IB, which, if you like, is our average input current, IN plus IP all on 2. So we've got an output voltage which now depends on I offset simply by specifying RP is equal to R1 parallel R2. Now, the nice thing about RP is we can include it if we're designing a non-inverting amplifier, in which case we would have our input going there. Alternatively, if we were designing an inverting amplifier, we'd ground that pin and we'd connect our input there. It doesn't matter, we can still include RP. It doesn't affect the gain of our circuit, it doesn't affect the behavior of our circuit, but it does greatly reduce the effects of non-zero input current.